Alright, we have a cantilever beam that we're going to take a look at with just a couple of loads on there that are imposed on the end. Right now, the overall thing here is we're going to find the shear and the moment functions so we can find maximum moments and all that kind of good stuff. But note that we start from those beam static equations that the rate of change of the shear is equal to the load and that the rate of change of the moment is equal to the shear. If you wanted to, you could put that into one second order differential equation. That second derivative of the moment is equal to the load is what that would all then be combined to be. And with that, you're going to end up with two and only two force boundary conditions. So let's set up our coordinate system. It's pretty common. We'll use go to the left and let that be the origin of our system. And we've got these two loads, concentrated force of 20 kips at the end at x equal to 0 and the applied moment of 100 kip foot. Well, that is what's going to actually establish the boundary conditions. Right, now some people want to say that the boundary conditions are these reaction values, but they're not. The whole name says reaction, reacting to the applied loads. In this case, the moment at x equal to 0 has to be equal to this smiley face moment, which makes it a plus 100 kip foot, whereas the shear at x equal to 0 is going to be immediately changed from 0 to the 20, and it's going in the negative direction for shear, so that means that that boundary condition is that the shear is equal to a minus 20 kips. Right? Those are the two actual force boundary conditions that we have in this problem. Right now, the next part is easy, right? dv dx equals w, but there is no distributed load, so therefore that means w is equal to 0. Right? We only have these concentrated effects at one specific location. Right? And that's going to make then finding the shear function particularly easy because alright, v is equal to the integral of dv, and dv equals w times dx, but w is 0, so hey, the shear is 0. No! We're integrating 0, which gives us a constant c1, and that tells us that, we have a boundary condition that v at x equal to 0 is equal, alright, the function is put in x value, but there is no x value there, so it's just equal to c1, and we set that equal to what it's supposed to be at that location, and that's minus 20, so therefore c1 equals minus 20 kips. How about that? Real calculus at work. Finally, a reason for you to take calculus, you betcha. All right here in statics. Alright, now find the moment function. M equals the integral of dm, and dm is equal to v times dx, and so once again we just found out that the shear function is equal to c1, which is itself minus 20, so minus 20 times dx, and we integrate that constant to be minus 20x plus a new constant of integration, c2. And what does that tell us? Well, nothing yet, but we have a boundary condition that the moment at 0, then evaluate our function here, we get minus 20 times 0 plus c2, and it has to be equal to a plus 100. So therefore c2 would have to equal a plus, well, 100. Right? 20 times 0 goes away, and that's 100 kip foot. Well, that was interesting. In this specific instance, C1 and C2 turned out to be the value of the concentrated forces that were being imposed on the system. That's not always true, but at this left edge like that, it is going to be that way if we set up the coordinate system that way. Right? So here's our answers. V of x equals minus 20 kips throughout, and the moment as a function of x equals minus 20x plus 100. Let's check it out and see if that works out right. We know it works out at 0, but v at, how long is this beam? 15 feet would be, well, the shear would be minus 20 kips. the m, the moment at 15 feet, well, that would be minus 20 times 15. That's a minus 300 plus 100 would be a minus 200 kip foot. Let's see if that's what really happens on the reactions here. Right? So positive shear would act down on the right at B, we'll call this, and the moment would be shown as so, counterclockwise. And if we sum forces in the y, we get minus 20 minus VB equals 0, therefore VB equals minus 20 kips. That's exactly what we have. How about that? Right? That's equal to the reaction out there. Some moments about point B, let's take counterclockwise positive. We have minus 100 plus 20 times 15 plus m sub b has to be equal to 0, and therefore m sub b would equal minus 200 kip foot. How about that? Wow, and that's exactly what we showed when we evaluated the function, that these reactions are going to turn out to also be equal to these internal force values right at that specific location when they're at the edge of the structure like that. Huh, that's pretty cool.